In this video, we're going to understand what a rate limiter is, what it's used for, the most popular algorithms, as well as real-world examples, so that by the end you'll have a really solid understanding of everything to do with rate limiters. So a rate limiter is simply a tool or a mechanism that controls the number of requests or actions a user or system can perform within a specific time frame. Think of it like a bouncer at a nightclub deciding how many people can enter at a time to keep everything running smoothly. Use cases include preventing overload, so they stop too many requests from overwhelming a system, ensuring it remains responsive and doesn't crash. It protects against DDoS attacks, so rate limiters help mitigate distributed denial of service attacks by controlling the flood of incoming traffic from multiple sources aimed at overwhelming a system. It also helps fair usage, so it ensures that all users have equal access to resources, preventing a few users from hogging all the bandwidth or compute power. And there's also cost management, so by controlling usage, it can also help manage and predict costs, especially in services that charge based on usage. So where should we implement it? So you could implement it on the client side, so this is on the user's device, such as within the mobile or web app, and this will prevent the client from making too many requests to the server, either accidentally or intentionally. And so the pros of this, it's immediate feedback. Users receive instant responses about request limits without needing server interaction, and it also reduces server load by limiting the amount of traffic that even reaches the server, which again saves resources. The cons is that it's easily bypassed, as users can modify or disable the limiter, rendering it ineffective. And there's also inconsistent enforcement, so different clients may implement different rate limiting, leading to an uneven control. You could also try and implement it on the server side, so this is backend servers that handle requests from users, and this protects the server from being overwhelmed by too many requests at once. The pros include it's a centralized control, it ensures consistent enforcement of rate limits across all clients, and enhanced security, as it's more difficult for attackers to bypass compared to client-side limits. The cons include increased server load, so rate limiting logic consumes server resources, as well as scalability challenges, as it may require additional infrastructure to handle high traffic volumes efficiently. It can also be done with middleware, so this is an intermediary layer between the client and server, often part of the infrastructure like APIs or gateways. And so this is used to manage and distribute incoming traffic before it reaches the main server, providing an additional layer of protection. The pros include scalable management, so it can handle high volumes of traffic more efficiently by offloading rate limiting to the main servers, as well as flexible policies, as they can easily apply different rate limiting rules for various services or user groups. The cons include additional complexity, so it introduces another component to manage and maintain within the system architecture, as well as potential bottlenecks, as if it's not properly scaled, the middleware itself can become a point of failure or congestion. So typically, middleware rate limiters are commonly used in large-scale systems, as well as within microservice architectures, and they come in the form of API gateways like AWS API Gateway to enforce rate limits, authenticate requests, and route traffic efficiently. The requirements can include defining rate limits, so we want to specify the maximum number of requests allowed per user or per IP address, or within a certain time frame, for example 100 requests per minute. And the reason for this is that it establishes clear boundaries, ensures fair usage, and prevents abuse and protects system resources from being overwhelmed. We also want configurability and flexibility, so this allows dynamic configuration of rate limits without requiring system downtime, and supporting different policies, e.g. a fixed window or a sliding window, and we'll be learning more about that later. And the reason for this flexibility is it enables the system to adapt to changing requirements and handle diverse traffic patterns effectively. And we'll also want low latency and high performance, so we want to implement the rate limiter with minimal impact on request processing time, because high performance rate limiting ensures that legitimate requests are processed quickly, maintaining a smooth user experience. So next we're going to look at some popular rate limiting algorithms, and the first one will be a token bucket. So imagine we have a bucket that holds a fixed number of tokens, so tokens can be added to the bucket at a steady rate, so say for example 1 token every second, and then each incoming request then requires a token to proceed, and if a token is available it's removed from the bucket and the request is allowed. However, if no tokens are available, the request is denied or queued until another token becomes available. And so you could implement some kind of retry queue here, which allows failed requests to retry, or it could be a dead letter queue if it proceeds to continue to fail. And so an example of this would be just typical API rate limiting, where a client tries to make a request to a server, and Stripe is a company that uses this token bucket algorithm, and we're going to dive into that later. The next is a leaky bucket algorithm, and so if you visualize a bucket with a small hole at the bottom through which requests leak out at a constant rate, and so incoming requests are added to the bucket, And if the bucket overflows, for example, if too many requests were to come in at once, the excess requests are then discarded or delayed with a retry queue if you want to be able to retry those messages again. And so this could be used in a place like streaming services to ensure a smooth playback experience. The next is the fixed window algorithm, and this works by dividing time into fixed intervals or windows, for example 1 minute long, and the number of requests is counted within each window. So once the limit is reached within a window, additional requests are blocked until the next window starts. And it's simple to implement, but it can lead to bursts at window boundaries. So if we look here, we can see that the maximum number of requests forwarded per window will be 10. So as requests come in, as long as it's below 10, those are forwarded on, but then anything after 10, those requests are dropped, and then each window that counter starts again. So it's allowed 10 requests, and then anything after that is dropped. But you can see here at the boundary between two windows, we can get a buildup of far more than the specified requests, in this case 10. And this is the downside of having such a simple algorithm, because it's bound by the time window. If there's a sufficient number of requests at either end of the boundary, we could potentially overwhelm our system, and that's something to take note when we're using this fixed window algorithm. And finally, we have the sliding window algorithm, and this is similar to the fixed window, but it offers more granularity. So instead of fixed intervals, it continuously tracks the number of requests in the past defined period, for example the last 60 seconds, and as time moves forward, the window slides, removing old requests and adding new ones. And this prevents the burst issue seen in the fixed window by distributing requests limits more evenly over time. And so you can see here where again we have a maximum of 10 allowed, and as the requests enter we can forward them, but then as we go over 10 we have to drop those requests, and as the window slides the number of requests in the window changes, and so we can continue to process as long as it's under the limit, in this case 10. And as we can see here, we've got a buildup of requests at one edge, but again, because the window is sliding, we are now only allowing the number of limits within that window. And so you can see here, we've solved that burst at the boundary problem that the fixed window algorithm had. And so looking at the architecture now, so it will start off with a client making a request. This request will reach the API gateway, which is responsible for managing and enforcing the rate limits. And the rate limiting logic is embedded within the API gateway. And this is a common and effective approach as it centralizes control and simplifies management. The API gateway can then communicate with Redis to verify if the user has available tokens in their dedicated token bucket. Redis is an excellent choice for this purpose due to its high performance and low latency, which is crucial for real-time rate limiting. If the user has sufficient tokens, the request can then be forwarded to the appropriate backend service for processing. However, if the token bucket is empty, the API gateway then responds with a 429 too many requests status code, indicating that the user has exceeded their rate limit. And then if we also want to be able to dynamically configure the rate limit, we could also have an admin dashboard that makes changes to the rate limiting rules. So this could then publish a message to a queue, which could be implemented with something like Amazon SNS. And then a worker, so something like a Lambda function, would then receive that message and then update the API gateway's in-memory configuration using AWS's API or SDKs. And so really straightforward, but again, what's important to know is the different type of algorithms, why we want rate limiting, and again, how to simply implement it in an architecture. And if we look at a real world example, so if we look at Stripe, so it uses a token bucket algorithm to do rate limiting. As we discussed, the algorithm has a centralized bucket host where tokens are removed on each request and tokens are slowly added into the bucket. And if the bucket is empty, the request is rejected. And in Stripe's case, every user has a bucket, and every time they make a request, we remove a token from their specific bucket. And Stripe again implements rate limiting using Redis. And then finally, additional discussion points could include burst handling. So you could implement a burst capacity in your token bucket algorithm to allow temporary spikes in traffic without immediately rejecting requests, which could improve user experience. We could also want to handle distributed rate limiting. So if operating in a highly distributed environment, you want to ensure that your Redis setup is optimized for distributed access, possibly using Redis cluster for better scalability and reliability. And then finally, you maybe want logging or alarm. So all rate limiting events, including allowed and rejected requests, are logged using Amazon CloudWatch, and this could provide visibility into the system's performance and user behavior. And so you could also set up something like CloudWatch alarms to trigger notifications when certain thresholds are met. For example, a spike in rejected requests, enabling proactive analysis and potential adjustments to that rate limiting strategy. So hopefully you got some value out of this video. If you did, please like and subscribe and share with a friend. It helps the channel out a lot. And if you're studying for technical interviews, make sure to check out techprop.app for the most up-to-date technical interview questions and solutions. And hopefully I will see you in the next one.